Yeah, so welcome everyone to this week's ICTS String seminar. We have Professor Dan Thies on from University of Chicago. He'll be talking about nonlinear bosonization of Fermi liquids, the method of coadjoint orbits. Over to you, so.
Thank you, and thank you for giving me this opportunity to give this talk at the ICTS. I'm going to talk about the problem of Fermi liquid and how the methods of coadjoint orbit can be useful there. So let me first give you the plan of my talk. I'm going to first remind the audience about the Fermi liquid theory as formulated by Landau. In particular, I want to emphasize an aspect of the Landau Fermi liquid theory that it can be thought of as a classical theory of describing the dynamic of the shape of the Fermi surface, and then we will see how the method of a coadjoint orbit works. In particular, in our case, the group that is relevant is the group of canonical transformations, which we will see why it's relevant for our case. And then at the end, we see how the method of coadjoint orbit leads to a natural reformulation of Landau's Fermi liquid theory. The co-authors of the works that we have put out in March on these topics, Luca Delacrétaz, who is postdoc right now in Chicago, Yi-Hsien and Umang Mehta, who are two students right now at the in Chicago. The theory of metals, or by extension solid state physics or condensed matter physics, can be said as started with Sommerfeld's theory of metal that Sommerfeld proposed in 1928. According to Sommerfeld, electrons in metals can be understood as a Fermi gas of free electrons. We can understand many properties of metal using this very simple picture. One example, for example, is the Wiedemann-Franz law, which is the relationship between the thermal conductivity and the electrical conductivity of metals. Sommerfeld's picture of free electron explains why the ratio between the thermal conductivity and electrical conductivity is always the same function of temperature for almost all the metal. But this picture of Sommerfeld left out one puzzle: why electrons would behave like free particles. If one estimates the values of the potential energy and the kinetic energy of electrons in a typical metal, where the potential energy is E squared over R, which is the Coulomb energy of interaction between neighboring electrons, and the kinetic energy is determined by the Fermi energy, eventually by the density of electrons. One sees that they are of the same order of magnitude. If they are of the same order of magnitude, then the question is, how can electrons behave like free particles, where the kinetic energy should dominate the potential energy? That puzzle was solved by Landau in 1957. In his seminal paper on Fermi liquid, Landau explained that the behavior, the free behavior of that we observe in metal is not the behavior of the original electrons, but is the behavior of the quasi-particle. So in Landau's picture, in momentum space, we have a Fermi sphere. Yes, so here is Px, Py. The Fermi sphere separate places where we have free field orbital state and the state that are empty. But imagine that we are at temperature that is much lower than the chemical potential or the Fermi energy. Then the modes that are excited are all the modes that are near the Fermi surface. So at room temperature, we are interested only at excitation near the Fermi surface. And by doing phase space analysis and dimensional counting, Landau's managed to show that these quasi-particles have lifetime, or the inverse lifetime, or the width of these quasi-particles are much smaller than their energy. Excellent. When the momentum of this quasi-particle approaches the Fermi surface, the energy goes to zero, but the lifetime, the width goes to zero even faster. That's why one can think about the gas of the very strongly interacting system of electrons, but at low temperature as almost a free gas of these quasi-particles. The Fermi liquid theory can be applied in many different cases. It has many different applications that range from helium-3 liquids, electron in metal, to neutrons in neutron star, and other applications. Now, we have mentioned that Landau's Fermi liquid theory is are sometimes described as a free theory, a theory of free quasi-particle. On the other hand, one should notice that we would see that the structure of the theory is very different from usual free field theory, like the free scalar field theory or the free fermionic Dirac field theory. And it is instructive first to look at the structure of the Landau Fermi liquid theory as proposed first by Landau and described in many textbooks. And we will see why this Landau Fermi liquid theory is very different in structure from all other free field theories. First of all, Landau's Fermi liquid theory is not formulated, at least in Landau's formulation, as a field theory. It's a theory that describes, actually, it's not that doesn't look like a quantum field theory. It looks like a theory that describes, it looks like a Boltzmann kinetic theory. So let's first take the case of free fermions. In this case, the Boltzmann equation is simply the Liouville's equation. The equation describing the time evolution of the distribution function of particle in phase space. F as a function of x and p coordinate, and momentum is also it's also a function of time. Liouville's equation is written in this way. The equation describes the behavior, can be thought of as the equation that describes the behavior of a collection of particles in phase space, x and p. So if one look in textbook, the way to derive this Liouville's equation is to follow the trajectory of the particle in phase space and count how many particles leaves or enter a given phase space volume. This term Vp here is the velocity of the motion of this quasi-particle in space, and this is the velocity in momentums. In momentum, that is, this is p dot and this is x dot. Okay, so here I have assumed that this particle lives in an external electric and magnetic field, and this term is simply the Lorentz force acting on the particle. V of p is the group velocity of this particle. Now, this equation allows one to follow from a given initial condition the time evolution of the system to all subsequent time. And one feature of this solution is the conservation of phase space volume, which implies that if the initial condition is chosen to have the form of a sharp Fermi surface, that is, if this function f is equal to either 0 or 1, as we would have in the case of Fermi Fermi gas at 0 temperature, then this feature that F can be either only 0 or 1 is preserved under time evolution. Because if we follow a given phase space volume as is moved according to the motion of the particle in phase space, we will this function F is preserved along the trajectory of this particle and remains either 1 or 0. So the Liouville's equation can be thought of as an equation describing the dynamics of the shape of the Fermi surface in momentum space. So let me draw this picture here. Suppose a t equal to 0. We start from the initial condition in which we have a distribution function, which in momentum space looks like a function that is 1 inside a certain surface and f equal to 0 outside that surface. So the picture drawn here has to be thought of as something that can also change in space. We go from one place, one x to another x, the shape of the Fermi surface can also change. Then we use the Liouville equation to evolve that distribution function with time. We can put that system in any external electric and magnetic field. And then at time t not equal to 0, we would see another picture. Against that picture that I'm drawing here can change in space, but we would still have the situation in which f is equal to 0 outside this surface and f equal to 1 inside this surface. And the Liouville's equation can be thought of as the equation that describes the motion of a surface in phase space that evolved with time. If there is any question during my talk, please interrupt me at any time.
So is the understanding that the volume of the entire phase space remains the same?
The volume should remain the same under the evolution. So the volume here would be the volume of this region integrated over all space.
Okay.
Yeah, over all x. So at each value of x, we integrate this region, volume of that region in momentum space, find this volume, and then integrate over all space, and that is preserved under time evolution. The Liouville's equation we can use this Liouville equation to compute physical quantities that are of interest for us. For example, we can compute the two-point function of density, rho t of x, rho t prime x prime. And the way to do that through the Liouville's equation is to look at the linear response of our system to a probe coupled to the density. So a probe that coupled to the density is the scalar potential that gives rise to the electric field, E. E here is just gradient of the scalar potential, A0. So the calculation of the two-point function of density goes through the linearization of the Liouville's equation. We write f equal f0 plus delta f. Solve this linearized Liouville's equation on delta f. And from there, we read out what is the change of the density. And that gives us the two-point function of the density, which is written here. So now this turned out to be equal to the real two-point function of density that one would obtain in free field theory by computing the one-loop diagram.
Sorry, what is the relationship between the density and delta F?
So rho, delta rho of t and x is equal integral over p dp d delta F of T x in P. So this delta F is the change of the distribution function in phase space. We integrate over P and get the change of the density at point T and X.
And then you're taking the Fourier transform.
Yeah, so this is, I'm solving the linearized, linearized Boltzmann equation can be solved in momentum space in Fourier transform. And that gives me some delta F as a function of A0, right? Here, let me not just write it down, rather trivial to find what delta F is in terms of A0. And then I integrate that with respect to P, and then get delta rho. That's the way to find linear response of a system on external to external electric field, and from that read out the 2-point function. So the calculation here is the calculation in a classical theory. Basically, we use classical equation, and this gives the correct 2-point function of the density in the limit when Q is much smaller than PF. When the probe electric field has the wavelength that is much larger than the Fermi wavelength. Nonlinear response can also be obtained in this using this method. We can solve the Boltzmann or solve the Liouville's equation not in linear order, but to higher order in the external field, and obtain their 3-point functions, 4-point function, etc. So this 3-point function that we would normally think as coming from a one-loop graph in this approach would boils down to solving certain classical equation of motion in non-linear order. Landau's Fermi liquid theory is next an improvement in to the free theory. In Landau's Fermi liquid theory, we have an ingredient that comes from the interaction between our original particles that are called the Landau parameter. So in Landau Fermi liquid theory, the modification boil down to the dependence of the energy of the quasi-particle carrying momentum P at the point X. That energy of this quasi-particle is the energy of a free quasi-particles, plus the modification that is due to the presence of a quasi-particle at a different momentum P prime. So the presence of a quasi-particle at momentum P prime influences a quasi-particle at momentum P and modifies its energy in a way that is local in space, but can be non-local in momentum space. Local in X, but can be non-local in P. Like this. So this set of parameter F as a function of two momentum P and P prime is called the Landau's parameter. And Landau conjectured that this is the only modification that we have to take into account in order to compute 2-point function of density, for example, using the this approach, the kinetic theory approach. So the kinetic equation now is modified. The group velocity of the quasi-particle now is the epsilon over dp, can depends on space x, and also this in this momentum. The force acting on the quasi-particle will also obtain another contribution from basically this interaction between the quasi-particle.
So can I ask a question?
Yeah.
So this f of p prime is supposed to be independent of the particular distribution or the temperature, or I mean, I wanted to know what is it that it is supposed to really be a function of.
So this one, yeah. So this one Landau is interested in the limit t goes to 0. So t would not appear in this function f. Function f does not depend on temperature. Now Landau also so in principle there could be term like the f square, etc. Here, which Landau say in this theory, if we are interested only in 2-point function, we can ignore this term. So this is now only a function of two momentum p and p prime, and in fact, it also depends. What is important is only the case when the two momentum p and p primes are on the Fermi surface, since we are at 0 temperature. And so here it's actually a function only of the angle between, in the rotationally invariant theory, it's a function of the angle between p and p prime. So in the
but I was just trying to get a picture of why is this the natural sort of modification? Maybe it's obvious, but
it's not obvious at all. So Landau, I'm not sure. If reading Landau, it looks like it's presented as a final, as a guess. Yeah, I think there must be a way that he arrived to this conclusion. And later on, people like Rykosov, Karkov, Terashinsky managed to derive this theory from perturbation theory. So imagine that we have a fermionic system with some interaction. They have been able to show that this picture arises by summing up an infinite number of Feynman diagrams. So you sum up Feynman diagram so when you compute 2-point function of density, they manage to show that the only important Feynman diagram can be decomposed into, can be thought of as summing up this ladder graph. And this is it's a very subtle analysis of the infrared behavior of this Feynman diagram, and it gives rise to the same formula, except here we now know what is this function. It turns out that this function in perturbation theory is the certain, it's roughly speaking 4-point vertex describing scattering of this particle coming with momentum p and with our particle come. So one pair of particles have momentum p, the other momentum p prime. It's a forward scattering amplitude.
Mm-hmm.
Okay. I would guess that if you have a disturbance on the Fermi surface at one point, it would be related by some correlation function to some other disturbance at some other point. So maybe the FPP prime is something like a Green's function, except that EP of X is not exactly F, but is the energy.
Yeah, it doesn't look that simple in Abrikosov, Karkov, Zelashinsky, though even what I'm writing here is a bit simplified picture, because they have to specify how momentum and how energy and momentum goes to 0 in this graph. It's actually this it's subtly which one goes to 0 first, which one goes to 0 later. Yeah, but this is what we know is the theory that describe the low energy dynamics of interacting fermions at momentum. So here the assumption here is that both momentum has to be smaller than Fermi momentum and omega much less than epsilon f. Okay, so yeah. Any more questions? Okay, so we see here that Landau's Fermi liquid theory is not a field theory. It doesn't look like something that arises from an action, a path integral. So we do not have a large toolbox of effective field theory.
Hello?
Yeah.
Hi.
Hello.
Sorry. So I just wanted to ask a question. So has there ever been any kind of non-perturbative derivation of this theory apart from these descending diagrams and so on? Like even numerically, are there any numerical things where without putting it in, you can kind of justify that this picture is good?
No, I don't think there has been that. Numerically, Fermi liquid, and this is just thinking on the fly. I think if one try to put in some lattice model, then normally there is a sign problem that prevents us from accessing the interesting Fermi liquid phase. But we can look at the experimental system like helium-3, very strongly interacting collection of atoms, but very well approximated by this theory. And so, at least at the level of two-point function, I think it looks like everything is at least at the level of things that one can measure in helium-3. Things seems to be described very well by Landau Fermi liquid theory. So so the diagrammatic derivation is to all order in perturbation theory. So it's non-perturbative, it's perturbative, but to all order in perturbation theory. But it's true that it's not a non-perturbative derivation.
So is the understanding that Landau kept the f function unknown and then matched with experiments and derived it that way?
This function is unknown. So this function, some of the Fourier, so this function of theta can be decomposed in spherical harmonics, and then we have these local Landau parameter, usually Landau parameter are called the expansion of this function f of theta in harmonics, and a few of these parameters, first one f1, 0, f1, f2 can be matched to the result of experiment in helium. They are known in helium. Actually, because of the spin, there is two set of function f and g depending on the spin channel, and the few first I think are known experimentally. And they are large. They are not small. They are the perturbative. Perturbatively, these would be smaller than 1 with the natural parameterization, but they are like can be as large as 10, 3, or something like that.
I have a question. Are these Landau parameters restricted because of some thermodynamics argument or maybe some stability argument in the? Apart from symmetry arguments.
Yeah, they are typical. So the stability give rise to a lower bound on this F. So, for example, well, in one parameterization, this F has to be larger than -1. Otherwise, the system would become unstable.
Okay. Thank you.
Yeah. Okay. So we have no way to think about, for example, systematic expansion of this theory in derivatives, like what we would do in effective field theory. We have no insight from the Wilsonian viewpoint on field theory, in which this we have a fixed point, and then we can think of relevant or irrelevant deformation from this fixed point. So if we have a field theory formulation of this Landau Fermi liquid theory, it will give us many ways to go beyond this theory. In particular, one application of a field theory formulation may be important in the problem of non-Fermi liquids. One example of a non-Fermi liquid is 2+1 dimensional fermion at finite density. That is, it has a Fermi surface coupled to a gauge field, to a U1 gauge field. This situation is believed to be realized in fractional quantum Hall physics at half filling. I will not have time to describe that to you, but it's believed that it is something that can be realized. And we have no way to, at this moment, we don't know the infrared behavior of fermions at finite density coupled to a U1 gauge field. There have been previous attempts to understand Fermi liquid theory as an effective field theory. A direct way would be to take an original theory of fermion and imagine integrate out all the degrees of freedom except one near the Fermi surface. So in this way of thinking, we would be concentrating our attention on degrees of freedom that has low energies, but right away we see that the situation is very different from the usual situation in field theory. The low energy degree of freedom has low omega, but the momentum of these degrees of freedom would still be of the same order of magnitude as PF. So low momentum doesn't mean low energy doesn't mean low momentum. So the effective field theory looks very complicated because we have to take into account scattering between particles at different points on the Fermi surface. So this delta function in the effective action, written here that this is a formula copied from a paper by Olchinski on this subject. We have a delta function where the particle momentum P1, P2, P3, P4 will be all on this Fermi surface, and they are not small. Counting the behavior of this P1, P2, P3, P4 as we do Wilsonian renormalization group is non-trivial. So if we try to do that, there is a natural way to see, as shown by Polchinski and Shankar, that the scaling properties of Landau and BCS coupling actually can be understood in this picture.
So omega is low because it is defined to be epsilon p minus epsilon f, correct?
Yeah.
Okay.
Epsilon minus epsilon f is the momentum, is the energy in small, but the momentum is still large and thin. In this formulation, another thing that that I will mention later, there unnatural cancellation between diagrams that makes the informers that somehow this picture may be not the best way to formulate Landau Fermi liquid theory. Another attempt is to bosonize a system. In 1+1 dimension, we know that fermion can be described, system of fermion can be described as boson. Yeah. In this bosonic picture, the current is the derivative, spatial or time derivative of the boson field. On the other hand, attempt to generalize the bosonic bosonization procedure to higher dimension faces with the same type of difficulty as in the case of direct formulation of Fermi of effective field theory. Basically, here we have instead of two Fermi points, we have in 2+1 dimension, for example, we have a line, Fermi line in momentum space. So a bosonization procedure typically would give us one boson per point in the Fermi surface. We cannot escape the problem that the Fermi surface has an extension, and so the bosonic the result of bosonization typically would have a bosonic field that depends on x and the angle theta here. And writing down a general effective action for this field it's not clear what are the rules that we have to apply to write down such an action. Another problem is that this field with different theta, they are not really independent of each other. If we turn on a electric field, one degree of freedom at one point in the Fermi surface can move to another point in the Fermi surface under the Lorentz force. And recently, Els and Thorken Senthil have tried to formulate this, using this insight from this motion of quasi-particle near the Fermi surface, try to attempt to connect these two anomalies. We will see that in our picture is our picture will be slightly different from what Els and collaborator wrote in their paper. Okay, so now let me formulate the question that I would like to address in this talk. It's a very restrictive question. Can one formulate Landau Fermi liquid theory as a field theory with an action so that the variation of this action give rise to the kinetic equation? The answer to this question is yes, we can do that. And the method that one has to use, the natural method to use here is the method of Coadjoint orbit. So the method of Coadjoint orbit has been applied previously to 1+1 dimension to reformulate the theory of non-relativistic fermions in 1+1 dimension as dynamics in terms of the dynamics of bosonic degrees of freedom. So we will see here that our picture can be thought of as just a multi-dimensional generalization of what Spenta and collaborator done a long time ago. Okay, so very short introduction to Coadjoint orbit. So just a few transparency. Consider a Lie group, G with the correspondent Lie algebra small g. If we have elements of the Lie algebra, we can exponentiate it to an element of the Lie group. We also know that the Lie algebra G, small g, supplies a joint representation of the Lie algebra on the Lie group. The joint representation is of a Lie algebra basically map any element of the Lie algebra to an operator of taking commutator in that is a joint representation, and exponentiating it, we get a joint representation of the group. So for unitary group, the joint representation looks something like this. F goes to U, F U minus 1. We can define the coadjoint representation in the following way. So first, we define the dual space G star. A dual space is defined so that any element of the dual space and the space, which is the algebra, can be for any pair of these, we can define a scalar product. And the coadjoint representation is defined so that if we rotate both small f in the dual space and big F in our algebra, the scalar product doesn't change. So the coadjoint orbit is defined as a result of the taking an element of the so we take an element F0 of the dual space and apply to it all possible elements of our group. according to the Coadjoint representation, and this F0 will be transformed into other elements of the on the dual space, and the trajectory of this F0 is the Coadjoint orbit, which is called O of F0. So O of F0 is the set of all points that we can obtain from a given point in dual space by applying the elements of our group. So the Coadjoint orbit is a coset of the group G and the subgroup that leave this F0 invariant. Okay, so the Coadjoint orbit is G divided by G mod H. Any question so far?
So
okay.
G star is the algebra, right? I mean, F0 is an element.
Not an algebra. G is an algebra. G is an algebra.
So G star is
the dual space. The dual space, that is the space that is for which any pair of G star element of G star and G is can take scalar product. For G star, there is no natural commutator on G star, but as we will see, there is a natural symplectic form on the Coadjoint orbit.
So G star is not any sort of generator as such.
It's not a generator. Yeah. So let me go to the application. So let me skip a few transparency and describe what is the group that we are going to be interested in. So the group that G that we are will be interested in is the group of canonical transformation. So let me describe first the algebra. The algebra of this canonical transformation is parameterized by a function of phase space X and P. You can think about this function of X and P as generating a small infinitesimal canonical transformation, transforming X to X prime and G to G prime as according to this equation, which can be interpreted as the evolution in time, in a time epsilon, infinitesimal time, using F as the Hamiltonian. You can see that this is this preserved Poisson bracket. And one can also check that two of the canonical transformation, infinitesimal canonical transformation generated by function F and G, commute to another canonical transformation with parameterized by a function commutator of F and G equal to the Poisson bracket of F and G. Exponentiating this algebra, we can get the group of finite canonical transformation. So the group that we are dealing with is a group of canonical transformation, and the algebra is parameterized by function of phase space, capital F of X and P. And now what is the dual space? So the dual space, again, is a function of X and P, and the scalar product is the integral of small f times big F. So this is now dual space G star. Now the physical interpretation will be the following. We interpret F as a physical observable. One example of F, for example, F equal P squared over 2m is the kinetic energy. If F is P squared over 2m, that would be kinetic energy. And small f will be interpreted as the state distribution function. The scalar product is the average of the distribution of the observable F in a state parameterized by the distribution function small f. The quantum mechanical equivalence is the trace of the product of the density matrix and F. So here we have a semi-classical version of the quantum mechanical trace that is integral over phase space. So the dual space is a space of state, and the Lie algebra is the algebra of observables. The action of the adjoint action on the algebra and the distribution function in our case looked exactly the same. Actually, this is an exponent of the Poisson bracket acting on either function f or small function small f. Yes.
So I understand there's a natural way that you can make a norm between the this distribution and the observable, but like any of the things you are going to say for really depend on this choice of norm.
The choice of norm, I think, is very important. Let me. It's very natural, but maybe it doesn't. But I think for physical interpretation, it's very natural.
I guess it's natural because it's equivalent to the quantum mechanical equivalent.
Yeah, and in the interpretation of this function f as distribution function is natural. Yeah, I haven't thought about your question, but maybe what I'm mathematically I don't need this, but maybe that is actually not that important.
But so we need some scalar product, right?
We need some scalar product, but this is the way that I have been thinking about this scalar product until now, but maybe one can just think about scalar product abstractly, and all that I'm going to tell you would still be valid.
I see.
I mean, for the thing that you have on this slide to be true, probably you need this particular scalar product, right?
For this slide, yeah. For this slide,
for the adjoint action to be like exponentiation of the Poisson bracket. For the coadjoint action, you probably need.
I will need the scalar product to be integral. Yeah, if I have integral over some weight times f small f, then this formula, the second formula, will be different.
Right.
Okay. Yeah. Okay. So now, why is it relevant for the problem that we are interested in? That's because we now have a way to parameterize the shape of the Fermi surface. We can think about state of a Fermi liquid that appear in the kinetic description in the as a point on the coadjoint orbit. If we take a reference state F0 as a ground state of the system, so a ground state, which is a state with spherical Fermi surface, let's assume that we are dealing with just rotationally invariant system. So the Fermi surface of this F0 is a state where f is a step function at PF. We can apply canonical transformation and transform it to a new state, which is parameterized by a function f, small f, which is still either 0 or 1, because it's just a canonical transformation. Doesn't change the phase space volume. And so the coadjoint orbits are still state with a sharp Fermi surface with the same total number of particles. That means that this kinetic equation, the Landau kinetic equation, Liouville's equation, is an evolution equation describing evolution on the coadjoint orbit. So the coadjoint orbit is a natural place where this Fermi liquid lives. Mathematically, the Fermi liquid theory describes a motion of a point on the coadjoint orbit. So our task is now to parameterize the coadjoint orbit and write down an action. Okay, so now parameterizing the coadjoint orbit. So let's make it simple. Let's work in perturbation theory, where F is F0 plus delta F. So,
can I ask a quick question for the previous slide? Sorry. Yeah. So why does it, you explained this, but I missed it. Why does it never exit the coadjoint orbit?
Because the Landau's Fermi liquid theory, so we start, it has a properties that the Fermi surface is always sharp. So all the state with the sharp Fermi surface can be accessible from the reference state by a canonical transformation. We can show that at least for small perturbation from the spherical Fermi surface.
Okay, thank you.
You're welcome. And so we can work in perturbation theory. So the we try to describe state with Fermi surface not very different from the reference state, from the ground state. We can parameterize it by as an action of element of the Lie algebra, which is now exponent. This phi here is a function of x and p. And if we follow the algebra, we will see that this state that we have here doesn't look like step function, but actually as a step function of PF. Now PF has a correction, P dot gradient of phi minus absolute value of P. And so this is now again a sharp Fermi surface, but the position of the Fermi surface has x dependence given by this function phi. We also mentioned that there is an ambiguity in parameterizing the point of the Fermi surface as a group element. Two group elements might correspond to the same point of the Fermi surface. Two group elements that differ from each other by multiplication on the right by an element of the subgroup that leave phi 0 invariant. So that leads to that we can use this to choose to fix a gauge in this function phi. It turns out that we can fix a gauge in which phi doesn't depend on the absolute value of p, but depends only on the direction of the momentum. So here phi is a function of only theta, which is the direction of p, not an absolute value of p.
Sorry, what is the gauge symmetry that is being fixed?
So here it is the multiplication of u by on the right by an element of the group that leaves phi 0 f0 invariant. Right? We can access the same point on the coadjoint orbit by an infinite number of different elements of the elements of the group by different canonical transformation. So this phi can be restricted to a function of x and the angle alone. And there is still a residual gauge invariance that one has to require that the theory is invariant under this residual gauge transformation. Okay, so now the action that give rise to the Landau's Fermi liquid theory turn out to have the following form. It has the Hamiltonian. So this Hamiltonian is the energy that correspond to a given Fermi surface, and that's where all the Landau parameters reside. Landau parameter would tell us how the energy of the system depends on the shape of the Fermi surface. But the first term has a very peculiar form. It's written. One can write in this way. See here, it's a scalar product of our reference state with u minus 1 dtu, where u is the elements of the group that rotate F0 to F. So this first term can be written also as in a Wessumino-Witten form as a two-dimensional integral of an integral of a two form, which turned out to be the Kirillov-Kostant-Souriau symplectic form that live on the Coadjoint orbit. For free fermions, the Hamiltonian is just a scalar product of our distribution function with the energy of the quasi-particle. Okay, so that's if we write down the equation of motion from this action, we can see that this is actually the kinetic equation. For free fermion, we reproduce the Liouville's equation, for example.
So, sorry, the symplectic form you're talking about is actually is this a canonical symplectic form on the coadjoint orbits of G star?
Yeah. So let me tell you maybe how usually in how one define it, how it is defined in mass literature, for example. So we have a coadjoint orbit here, and then our point F0. Oh, there's a point. So we don't have to think about F0. Let's consider a point F. Okay, so this two form would be something that put two different tangent vector, delta F1, delta F2, with a number. So this omega, this number is defined through these equations here. So delta F1 and delta F2 are the result of small rotation of this F by elements of the Lie algebra, capital F1, capital F2. So we rotate F using infinitesimal transformation and get these two vector. And we define this symplectic form as the scalar product of the commutator of F1, F2 with F. So now here one have to check that this formula doesn't depend on which F1, capital F1, which capital F2 we choose. There is ambiguity. And also we have to show that this is a closed form, and both can be shown. So that is the definition.
Yeah, I mean, about the closeness, it looks as if we can show it from the Jacobi identity, right?
Yeah.
But I mean, is there any easy way to see the non-degeneracy of this two form?
Non-degeneracy.
Yeah, I mean,
yeah, I think it's one can see that one can see it non-degenerates on the coadjoint orbit. Maybe I don't have, yeah.
Okay.
Yeah, it's yeah, I think it's non-degenerate. Yeah.
Okay.
Yeah.
So an example of F1 or so an example of capital F would be p square by twice m, as you were saying before, right?
Yeah.
So if you take capital F1 to be p square by twice m and F2 to be something else, then
yeah.
And F to be the Fermi surface function.
Mm-hmm.
Then what sort of transformation would this induce? I mean, so what would the omega?
Yeah, so F1 e to the F1 would make the Fermi surface into slightly different shape. This one is another, F2 would be a different shape, another shape. And so it's actually non-trivial to think about what this form, what information this form is. It actually tell us this term correspond to this term actually can be is the Berry phase that a Fermi surface obtains when it changes its shape. So let me write it in perturbation theory. Suppose I expand this action to quadratic order. This action, this Weissenwiener-Witten term is this term, phi dot times n gradient of phi. So n is along the momentum n. So phi is a function of x and theta, and n is the vector along the direction theta. So this action, the quadratic action, is an integral of over theta of action of chiral, each of chiral boson, one chiral boson for each theta. And the density operator is also integral of the density of the chiral boson. And one can check that the 2-point function in the free fermion theory, given by this one loop graph, coincides, is reproduces exactly by this quadratic action. We can also go to nonlinear order and check that the result of quite more complicated algebra reproduce exactly the 3-point function. So in a free theory, in free fermion theory, the 3-point function is the sum of 2 diagrams of density with the fermion loop going in different direction, and the result of this calculation is exactly equal to sum of 3 graphs in the bosonic theory. And this is also non-trivial in the following manner. These 2 diagrams almost cancel each other exactly in the limit when the momentum q of the external legs goes to 0. This non-trivial cancellation is natural in the bosonic picture. Okay, any question?
I have a question. Would you finally also do the finite temperature thing, or?
So the finite temperature thing is seems to have yeah, let me maybe I say it right away. It seems to have in the case of free fermions, seems to be difficult to obtain in this picture because of seems to have the effect. This action seems to have a UVIR mixing in the case of free fermion. For fermion coupled to a gauge field, the non-Fermi liquid, amazingly, the situation is seems to be better. It seems to have no UVIR mixing.
So the only way to get at the finite temperature theory is via the Polchinski method, or?
No, in this bosonic method. So we would take this bosonic action that we have here and then put it at finite temperature and ask whether we can reproduce thermodynamics.
Yeah, but you are saying that it's difficult to do it this way.
If for Fermi liquid or free fermions seems to be complicated in this bosonic picture, because roughly speaking, in what we have here, we are able to describe particle hole excitations with the particle and holes that are not separated, not very far away from each other in momentum. So these bosonic degrees of freedom in the fermionic picture are particle hole excitations. So we in this action, we naturally describe particle hole excitation with small separation between particle and hole. At finite temperature, all possible pairs of these particle hole are excited, even one with large separation. So this action seems to be less suitable for this problem. This bosonic picture.
Can I make a comment? But I think it's still correct to integrate dt from 0 to beta in Euclidean time, right? It's still correct formulation. It's more difficult to manage it because of this IR-UV mixing. Is that a correct comment?
I think in
In
principle, yeah,
yes.
in principle, yeah. Maybe I mentioned that now. So, one can think about this algebra in the same way as what was done by Spenta, the collaborators in 1991. Instead of thinking about the canonical transformation, maybe the more general way to think about our approach is to think of an algebra formed by fermion bilinear, like this operator here, written here. This operator form a closed algebra if Sime-Seidecker commute canonically. In the long wavelength limit, this algebra is the algebra of canonical transformation. But if we go away from the long wavelength limit, we get Moyal brackets instead of the canonical, the Poisson brackets. So maybe in order to get the UV, the necessary UV information needed for finite temperature calculation, we need to deal with these algebra. And the Coadjoint orbit method is probably in some sense a coherent state representation, path integrate representation of the true theory. Another, so in this way of thinking allow us to think about extension like a spinful Fermi surface, where we include in the theory also spin operator carrying spin, or the BCS theory, in which you extend the algebra to include also operator that have charge 2 or -2. Okay, so let me conclude. The method of coadjoint orbit provides a natural way to write down an effective theory of Fermi liquids. It leads to a non-linear action, a non-linear bosonization of the Fermi liquid. It managed to reproduce all linear and non-linear Fermi liquid response at 0 temperature, and perhaps it's a suitable starting point to study non-Fermi liquid. We can imagine coupling this bosonic action to a U1 gauge field and try to understand the behavior of this theory in the infrared. Thank you very much for your attention.
Yeah, let's thank Song for a wonderful talk. Thank you. Are there any questions?
Yeah, I have a question. Like, your starting point for all this was essentially the same starting point as Landau, that is the classical theory, right? I mean,
yeah,
you assumed that X and P can be simultaneously defined. That's correct, right?
Yeah.
So I would suppose that a more natural starting point would be a quantum theory where X and P can't be defined simultaneously, and I mean, the sort of starting point that Polchinski had in mind. So what is the difficulty with that approach in getting all this?
The difficulty, well, let me step back. The difficulty with the Fermi liquid theory is that we don't know, with the field theoretical approach to Fermi liquid theory, is that we didn't know what are the degrees of freedom. So in the Polchinski approach, Polchinski and Shankar and Benfato, Galavotti before that, we are trying to formulate a theory where the degrees of freedoms are the fermionic operator. And now the problem with this approach, first of all, the natural formulation would be in momentum space, not in coordinate space, because only in momentum space, it's natural to say what is low energy, what is low energy, and what is not. So Pochinski, Shankar always write the action in momentum space. Now, technically, this is make things much more complicated. We do not know how to couple naturally probed fields, for example, electromagnetism. Coupling gravity to that theory would be even more complicated. We don't know how to do that. And so, that might be technical problem, but I think more of a problem is that this action include in itself certain cancellation between certain diagrams. So some diagram like this cancel with the same diagram with permutation of fermion. So it looks like it's not a natural degrees of freedom. The degrees of freedom that Landau chooses seems to be more natural. But then your question of the semi-classical, whether we can go beyond the semi-classical approximation in Landau. So one thing that one can do is to promote this group, canonical group, to a group of fermion bilinear. So now we have a new group, this G, where the commutation relation between F and G is now given by the Moyar product. So this seems to include at least some non-semi-classical information of the original theory.
Sorry, I'm a bit confused. I mean,
can I make a comment? Just a minute, please. Soon, can I make a comment?
Yeah, sure.
What you just said. So if you look at this bilocal operator, where the psi and psi dagger are operators, then from this you can build the Wigner distribution, right? By shifting x and y and writing a phase. So you get essentially what I'm saying is you take OX.
Some kind of
that's right. That's right. I mean, you shift x by plus q upon 2 and y by minus q upon 2, write a phase e to the IP
something like this.
Yes, that's right. Exactly. And so you get essentially an operator O, right?
Yeah.
Now, if you look at the integrand, that can be understood essentially as, if you look at the Heisenberg-Weyl group, then this integrand can be understood as psi dagger, the element of Heisenberg-Weyl group, times psi. So the Heisenberg-Weyl group essentially is the generalization of the classical Poisson bracket, and then using coherent state representations, one can create an exact formula for the quantum mechanical formula for the action. So that's possible. I mean, that's done. That was done by us actually a long time ago. Also.
Yeah.
I just wanted to say that quantum mechanically also we can deal with this exactly.
Yeah.
No, I was just confused about one thing. I mean, I suppose your coadjoint orbits were defined on the Fermi surfaces. There were transformations on the Fermi surfaces, right? Is that right?
The state, the semi-classical approximation of state would be viewed as a Fermi surface. That's right.
Yeah. So, I don't understand how you are getting position space variables here, because you seem still to be dealing with the Fermi surface and it's the momentum space deformations.
So in this picture, I would do the following. I would take some state, some kind of ground state. So this ground state is the ground state of a free state with field Fermi surface, and then act on it operator U. So rotate. So we construct coherent state, which is obtained by this state 0 by acting on it, the exponents of f. The f is an exponent of linear combination of this O. And that would be a set of coherent states. Semi-classically, of course, this would be state with sharp Fermi surface. Quantum mechanically, of course, then it's some kind of a coherent state. So that's the way I think about this coadjoint orbit formalism quantum mechanically. Each point in the coadjoint orbit corresponds to a coherent state.
And again, f can be defined as p square by twice m in some cases, right? So what would the corresponding coherent state be for that?
I'm sorry, I missed your.
F you said could be defined as p square by twice m in some cases. I mean, an example of f would be p square by twice m. Isn't that correct?
An example of f?
Yeah, f, e to the
yeah.
f, e to the f.
Yeah,
that
p
f
square.
An example of capital F would be p square by twice m. Isn't that correct?
P square over 2m?
Yeah.
Yeah.
So in that case, what would the coherent state look like?
So this is p square over 2m is doesn't change. Exponent of that doesn't change the ground state. Actually, we leave the ground state invariant. It just changed the phase, right? It's we have chosen the ground state to be a state in which each just brought all the state inside here is filled. So if we take e to the alpha f, where f is equal to that, we get just a phase which is e to the sum over p square over 2m inside this Fermi surface time the same state. So we need some f that is different from p square over 2m. It needs to have x dependence. You have to have some x dependence to give us something different from the state we start with.
I have a question. Can I ask a quick question? So this algebra of canonical transformations, how do the coadjoint orbits look like geometrically?
Yeah, geometrically, it actually these state with so if the reference state is a state with a sharp Fermi surface, and the coadjoint orbit is the space of all possible shape.
I see. Mm-hmm.
Total moment, the total volume should be invariant, and also the topology, I think, cannot change. We still need to have just one single surface with no hole inside. Yeah.
So is it an infinite dimensional space or the coadjoint orbit, or is it finite?
Infinite dimensional.
Infinite dimensional, okay. And in the fermion bilinear, what is the coadjoint orbit? How does it look like?
Yeah, that's, I would assume it's similar and it's a deformed somehow, but I don't have I don't have a picture in my head, unfortunately.
Okay, okay.
Yeah. Mm-hmm.
Also, this coadjoint, this Fermi surface, these deformations are deformations are in the momentum space themselves, right? I mean, they are not going outside the momentum space.
Yeah, but each of the Fermi surface shape can depends on x. So it's actually each of these shape is a function of x. So each coordinate x, the shape can change.
Oh, for each x, there is a different Fermi surface, you mean?
Yeah. Yeah, but it's a smooth function of x. So it's like a tube. So in 2 dimensions. So maybe it's easy to see. It's it's like a tube. That infinite in coordinate and then have a shape in momentum.
Yeah, I have a question about about this method of, this new method of based on this new method based on the formulation of coadjoint orbits and KKS symplectic form. I mean, how does this help in the context of non-Fermi liquid theory or understanding non-Fermi liquids?
So it would help in the following way. So I have a way to write down an action. So this is my field, and then for example, one way to make Fermi liquid is to couple the theory to external gauge field, E1 gauge field, a mu. So that can be done naturally. Usually, so the problem before was always that there is no, for example, in the fermionic picture, so in the fermionic picture, we have the analysis of divergences of diagrams, complicated diagram like this, was always very subtle, because one has to take into account the cancellation between different diagrams. So we hope that we haven't done the power counting carefully in our theory, but at least some sort of subtlety in the usual picture disappeared now. Of course, the fact that our theory is truly a field theory helped. That it's a truly effective field theory with well understood degree of freedom. Degree of freedom now is understood as living in a coset. So that's all make everything. At least thinking about that. At least for me, thinking about that is much more natural.
Okay. Yeah. Thanks.
So I just had one question. So when you couple it to a gauge field, is it dynamical or background? I can understand.
It's a dynamical gauge field.
Dynamic.
So for some dimension, we would add this term, but this in 3+1, it's E square goes to infinity in the infrared. That problem is even more serious if you have a Fermi surface.
I see. So would you then enlarge your group of canonical transformations to include gauge transformations, and then just look at a different Lie group and a coadjoint orbit for that? Or I mean, is that how you would approach this problem? Or
gauge transformation is a subgroup of canonical transformation.
Oh, okay, yeah.
Yeah. So one can do that without. We can gauge it very easily.
I see. Yeah. Okay. Right, because you're looking at distribution functions, the gauge transformations are already present. Yeah.
Yeah.
It's just the action on the gauge field that you also have to incorporate.
Yeah.
Right.
Yeah. Can I ask a question? This whole formalism of creating ripples on the Fermi surface semi-classically by group action seems to be, in some sense, near some integrable type of system. Now, one of the things which would be very interesting is if I can take a Fermi surface. I don't know the Hamiltonian of the system or anything, but I can make some sort of a complicated group transformation so that I can have a chaotic type of motion on the Fermi surface. This is the sort of thing which would be very interesting, I think. The reason I'm saying this is the following, that all this work that we did in the early 90s was motivated by trying to understand black hole microstates in string theory. And it never worked out because all these models turned out to be, integrable or quasi-integrable, etc. And today we know that if you want to model a black hole, you need the system to have classical chaos. So that's why I'm asking this question that suppose I don't know the Hamiltonian, but is it possible to conceive of generating some sort of a very complicated, chaotic motion of the Fermi surface? Just it occurred to me when you were speaking, so I asked this question.
Probably that would happen in, so suppose I take a Fermi surface and then deform it to a state like this. So this state would have finite energy compared to the ground, and then leave it evolve with time. In interacting fermionic system should then goes to equilibrium, thermal equilibrium somehow. So that presumably, yeah, but I'm not sure how it would look like in probably on Coadjoint orbit, as you said. Probably first see the chaotic motion on the Coadjoint orbit, and then somehow we need, after coarse graining, that we would have a finite entropy state. That's my
okay
speculation.
Thank you.
So Son, you mentioned that this Hamiltonian term that you add to the usual kinetic term, that contains all the information about the Landau parameters, so that presumably comes just because it generates. I mean, you get the delta F that that you get will be now have a contribution not only from the shape. I mean, the shape will now have a dependence on the you can give a prescribed dependence for the shape depending on your Hamiltonian. Is that, I mean, so my question is, does the specific form of the Landau parameterization, is that something very natural from the point of view of this Coadjoint orbit? That you get this bilocal form in momentum space f of pp prime?
Yes, so basically it's the following. So in the, we can think about the perturbation of the Fermi surface and parameterize it by some height function. Some height function is a function of theta. And then the Landau term would be a quadratic function f of theta, theta prime h, theta h, theta prime. That's the Landau.
The Hamiltonian function, I see.
Yeah. Quadratic function of the height. Yeah.
But there's nothing which says that it had to be like this, meaning that's what the Landau, I mean, I was trying to see if there's something very natural about the Landau parameterization.
Taylor expansion, right? If your Taylor expands the energy, you assume that energy is a smooth function of the shape. And if Taylor expand it, of course, it's a linear term, quadratic term. So that the quadratic term would be
but normally these things you would, as you said, it depends on x as well, right?
Yeah.
So you might have thought that this f can also depend on x.
X and x prime, but since interaction, we assume that interaction is short range, and so everything should be linear in x. So here, this function is a function of x. The dependent on x should be linear, should be local, should be local in x. I'm sorry. So this is just one integral over x of this. This h doesn't live in two different points. We are in.
So that's a physical requirement you're putting in.
We are interested in long wavelength limits, and so
okay. So in the long,
of course, there is some like derivative terms that one can write down also that can be thought of as just expanding this non-locality in derivatives.
And
Landau
F itself, capital F, cannot have any X dependence?
F is dependent. So F capital F.
Yeah.
Capital F is capital F. If it had, so capital F doesn't have X dependence.
That's sort of put in by hand in some sense, or it's...
translational invariant.
I see.
So if you write down an effective action, which is translationally invariant, F cannot. If F has the X dependence, then it only comes from the
variation of the height.
Yeah, and then we can use that to expand in H, and that would be a cubic term, for example.
Okay.
Yeah. So it's Landau parameter is just the first term in the expansion over the height and the in gradient expansion.
Okay. Okay. Thanks.
So what I understand is your method is a way of getting the coadjoint method, coadjoint orbits method, to kind of formulate the deformations of the Fermi surface locally. Is that correct?
Yes, as a field. To parameterize the deformation of the Fermi surface is a field.
Yeah. So is there any way you can get it from some fundamental quantum theory? I mean, this coadjoint, I mean, can you get your starting point from some more fundamental starting point?
I'm not completely sure. This be beyond what something that maybe maybe what I try to say here. We can think about the Coadjoint orbit in the quantum language as coherent state built out of the group of fermion bilinear. I think it should be possible to think that way, at least for weakly interacting fermionic system.
You mean in the sense that the way the coherent states kind of represent classical, I mean, they represent quantum fluctuations about some classical form or wave form or something like that. Is that correct?
Yeah, we can just reformulate I'm extrapolating, but I think one should be able to reformulate. Simplest case would be free fermions path integral in terms of path integral over these coherent states. And the semi-classical approximation would go back to Coadjoint orbit.
But in order to define a coherent state, you would have to have some sort of creation operator which you have to exponentiate and then act on the vacuum state. What sort of creation operator would you envisage here? Because a coherent state obviously has to have some sort of e to the a dagger or something like that, right? Times some function, some coefficient. So what sort of creation operator would you kind of think would appear here?
I'm not sure. I know this. Probably it's some coherence. It's similar to the SO3 type of coherence that we have. We have just a state. Maybe let me not just speculate too much. It's a question we haven't how to define the coherent, how to exactly define the coherent state. What are the what is the over completeness condition, etc. This we have not explored.
So can I say something?
Yeah.
Can I make a comment?
Yeah,
So,
sure.
Thank you. So if you take this algebra, this W infinity algebra, then that is your algebra of canonical operators. So you can't really distinguish between what is P and what is Q, and that is the whole difficulty. But mathematicians have taught us how to create coherent states for any Lie group. That is just to take a given vector and act by a group element, and then you just do the standard Feynman path integral, and it works out very nicely. Yeah, it can be done. That's all.
Yeah, but the reference state that we have is not a vector of the algebra.
That is right. That's okay.
Yeah.
That's okay.
Just have I want to take a reference state to be the ground state of the free.
Exactly.
Yeah.
That is correct. That is correct. So in all these models, at least the ones we looked at, that's just the ground state of the fermion system, basically. Yeah, of the free fermion system.
Usually, the coherent states in field theory are the eigenstates of the annihilation operator. So
that's the same thing, because, excuse me, that's the same thing, because in ordinary field theory, it is just the Heisenberg-Weyl group of A and A dagger. Yeah.
No, I was talking about a different thing. So since you're talking about deformations here, suppose you have a certain deformation fx, and it's the eigenvalue of some annihilation operator acting on some coherent state f. So is that the coherent state you're looking for, which is the eigenstate of the annihilation operator with eigenvalue fx, which is some deformation?
But the whole point is that there is no such notion of creation and annihilation operator which you can separate out in more complicated systems like the SU2 Lie group, for example.
And where is SU2 coming in here?
No. This is an example.
Example. Yeah, if you can define the spin coherent state. Spin coherent state would be a state which is the analogy of, so here the Coadjoint orbit, the simplest Coadjoint orbit is the Coadjoint orbit of SO3 group. I think this Coadjoint orbit of SO3 group is a sphere, and the each of the point in quantum theory would correspond to a spin coherent state, which is the eigenvalues of the spin operator times the direction in one direction in space. So that's how it should work.
Even the spin operators can be defined in terms of creation and annihilation operators in some basis, right? I mean, in some representation, even the spin operators can be represented in terms of creation and annihilation operators, right? So, I mean, unless you have some sort of operator acting on some vacuum to give something excited, some excited state, I don't see how you can form coherent states.
We take a reference state and then apply the
there are these things, sorry. Parallel of, I think they are called parallel of generalized coherent states, right?
Yeah. But I mean, what I'm saying is, unless you have some sort of creation operator acting on the vacuum state to give some excited state and higher excited states when you act on more and more creation operators, I don't see how you can build up a coherent state without these.
Yeah, we can define a state like this. G. Doesn't have to be, we don't have to think about creation annihilation operator.
And how would UG acting on 0 generate the G?
It's just UG is an element, is exponent of this operator, for example, in our case. So in the case of the spin, it would be e to the power of I n times spin. It's a rotation. In the case of SO3, for example, it's a rotating. It's a operation of rotation acting on some reference state. This reference state can be chosen as a state with spin pointing in the z direction. You get another state, G. Then, so that's how one can get the coherent state on a sphere.
So for instance, if you take the spin half system, for instance, and you take the spin up direction to be the ground state and the spin down direction to be the excited state.
Mm-hmm.
That is how these spin operators, S spin operators, would act on the ground state to create the excited state up. That's all of what I'm saying.
Yeah.
I mean, so the entire thing can be reformulated in terms of creation annihilation operators.
Yeah, if you want to see these are the creation annihilation operator that acts on, say, Fermi fermions to move them from inside the Fermi surface to the outside of the Fermi surface. So, this bilinear operator has creation and annihilation operator like the spin operator in spin half, like here, psi decker sigma psi. You can think about that also that way.
But in order to get the coherent state, I suppose you would have to have not a bilinear, but a linear in terms of the creation operators multiplied by some sort of coefficient.
You don't have to do that. You can do that in the case of the file group, but you don't have to do that. In the spin case, you can also do that, but so I would think that for SU3, for example, that would be quite cumbersome to do.
Right. Perhaps we can continue this discussion offline if the audience doesn't mind. Are there any other questions for Son?
Just a quick question.
Sure.
So is it possible for the dynamics to encompass a few coadjoint orbits, finitely many coadjoint orbits, rather than just one? Is it possible to conceive of such a situation?
Can one get the system to move from one coadjoint orbit to another coadjoint orbit?
Yes, maybe a finitely many coadjoint orbits.
I don't know how to do that. Yeah.
Okay, never mind.
Mathematically.
But perhaps if we start with a
different,
yeah, or a disjoint Fermi surface or something like that.
Yeah.
This Fermi surface is specified by the fermion number, in this problem, for example. So if you have different fermion number, it will be a different coadjoint orbit. And I don't think you can really jump from one to the other. Like for SU2 also, there are infinite number of coadjoint orbits labeled by the value of the angular momentum, right? It's a conserved object. So you stay on that orbit. I think so. I mean, I think that's perhaps the answer to your question, but maybe Son can clarify.
Yeah, we don't have relative, we don't have operators that create a single fermion operator in our language.
But even keeping the fermion number constant, there are more constraints, I would imagine, like topology you mentioned. You wouldn't want the Fermi surface to change topology to an annulus or something like that. Right?
Yeah, or
even
separate two Fermi
or
separated
into two blobs. But I'm wondering what is the full set of these constraints, because there is would it be possible? I mean, for instance, if you just kept topology and fermion number as the only constraints, you could imagine deforming, not small deformations, finite deformations where the Fermi surface moves away from the origin, meaning it kind of maybe is in like an arc around the origin. That's possible just in terms of area preserving or volume preserving canonical transformations, and which also preserves
like
the
this.
But yeah, like that.
Like that, clearly, there's you can do
but isn't that
steps? Yeah, you can do a finitesimal step, and
but it seems that that should be somehow unphysical. No, that somehow you don't. Your kind of the Fermi surface doesn't have the zero of. There is something preferred about the origin also in momentum space, isn't it?
No, there's nothing. Yeah, we can easily make a canonical transformation that shift the Fermi surface.
Yeah, no, that I understand. You can make that canonical transformation, but physically, isn't there something more? I'm just.
It is just the translation. If one turn on electric field, for example, we can shift the whole Fermi surface.
With the electric field, yeah. So that you're saying you can remove the origin of. You can
origin is nothing.
But in that sense, even like the pinching of a Fermi surface into two, that even though it is sort of a singular limit you have to go through, but you can imagine going to a pinched Fermi surface and then maybe some droplet kind of.
Yes. That's done. Yes, that's done. So can I say something, Rajesh? Soon?
Yeah.
This coadjoint orbit of this problem is not only characterized by the fermion number, but by an operator constraint, which is basically O square equal to O.
Yeah,
O square is an operator multiplication equal to O. That's a very complicated constraint. And classically, it just becomes what Son said, this F square equal to F. So F is either 0 or 1. Yeah. So, but quantum mechanically, it is a very complicated constraint in terms of the Moyal stuff and all that you know very well. So.
Yeah.
But this,
So is the statement that canonical transformations do not give rise to such pinched surfaces, or we consider only coadjoint orbits which do not have such pinched surfaces? I mean, how regular are these orbits? Suppose we start with a good regular point, like this.
Classically, if we have smooth canonical transformation, you would never pinch the surface.
I see. Because I was thinking that suppose at least in say SU2 or SU3, if you look at one of these Borel subgroups like this, something that just has an upper triangular or lower triangular matrix, and then you keep exponentiating that, that may give rise to some kind of squeezing or pinching, right, on the source state. But that does not happen.
Infinite, here you want an infinite pinching, right?
Pinch.
I think
and this area preserving nature is what prevents that, is it?
No, area preserving is
still okay. Yeah,
it's still okay. The pinching, I think physically what happened at the pinching is that the nature of the degrees of freedom changes at that particular point. That it's no longer just a usual Landau Fermi liquid theory, but there is some degree of freedom. In addition to that, exactly at that point, and when we go away, go back to Landau's Fermi liquid theory.
I see.
So do you take the Landau coefficients or the Landau numbers as inputs, or do you derive them out of your formulation?
Here it's input. Of course, that's the point of view one has to take in effective field theory. That there are some input in the effective action that cannot be computed. But if we start from a free theory, for example, free fermions, we can match this coefficient of the bosonic theory to the known Fermi theory. If we know the fermionic theory, we can match the coefficient of the bosonic theory to these to reproduce the true result.
So your motivation is not to derive the Landau Fermi liquid theory from some other starting point, but to give an alternative formulation.
Yeah, one way to think of, one motivation is to have a general way to write down the effective action of a system with Fermi surface. Like in QCD, we just need to know the chiral symmetry to write down the chiral Lagrangian. We don't need to know exactly how to derive from QCD Lagrangian the chiral Lagrangian. Here, I want to have a general formalism that allows to write down an action for the Fermi surface.
Just a small comment on the previous question. Another situation, I guess, a trivial situation where you will have multiple coadjoint orbits to deal with is when you have many species of fermions, I guess, right?
Many species of fermions, like
yeah, just some flavor symmetry.
One of the situations we thought about is fermion with spin 1/2 fermions. And in the case of spin 1/2 fermion, we can expand the algebra to include the spin operator.
Right. But if there is some internal symmetry, that would also work out.
Yeah, that can be because in the spin, if the deviation from in singlet state is small, we can assume this operator to have small expectation value and then expand the action only to quadratic order over this. That makes it simpler.
Right. Okay. Thanks. Are there any other questions for Son?
Thanks very much, Son, for your patience.
Thank you. Thank you for.
Thanks a lot, Son. 2 hours.
Very
clear. Thanks a lot. Thanks a lot.
Okay. Thank you very much.
Thank you.
Bye.
Bye.
Bye. Bye.